according to the given question, a solid sphere of radius r is rotating slowly at a constant angular velocity ohm in a large body of quiescent fluid. Develop expressions for the pressure and velocity distributions in the fluid and for the torque Tz required to maintain the motion. It is assumed that the sphere rotates sufficiently slowly with constant density and viscosity system. Neglect the effect of gravitational forces. Since there is no driving force in r direction, Vr is equals to 0, and as the flow is axisymmetric, V theta is equals to 0, so only V phi exists, and V phi is a function of r as the velocity reduces as you go up, as you keep on going away from the sphere. So V phi is a function of r, and similarly V phi is a function of theta, because V phi is a function of theta because velocity changes as you move across the theta direction on sphere. So coming to Navier-Stokes equation in spherical coordinates for a system of constant density and viscosity, solving for r momentum equation, dvr by dt tends to 0 as the system is in steady state, and this is 0 because Vr doesn't exist, and this also doesn't exist because Vr equals to 0. Similarly, minus coming to the right hand side, minus dou p by dou r plus mu into viscous terms. All these viscous terms are eliminated, and this finally simplifies to this. Similarly, coming to theta momentum equation, dou v theta by dou t is equals to 0 as the system is at steady state. Similarly, v theta is equals to 0, so this is also 0. V theta equals to 0, this is also 0, and V theta is equals to 0, this is also 0, so only this term remains, and this simplifies to this. And phi momentum equation, with Vr equals to V theta equals to 0 and dou by dou phi equals to 0 because of axis symmetry, it simplifies to this form. And as this form is difficult to integrate, we assume V phi is equals to f of r into sin theta and solve for these terms, dou V phi divided by dou r and dou V phi sin theta divided by dou theta. And after solving this, we substitute dou V phi by dou r and dou V phi by dou theta in the above equation, above phi momentum equation, and after simplification and dividing by sin theta by r square, this reduces to this. So now, as this cannot be solved easily, we know that f is a function of r, we assume f of r is equals to r power m, and after you substitute this in r square f double dash plus 2rf dash minus 2f equals to 0, we get this equation. And as we know that rm can't be equals to 0, m into m minus 1 plus 2m minus 2 will be equals to 0, and m is equals to 1 comma minus 2. From this we can see that fr is equals to c1r plus c2 by r square, because m is equals to 1 and minus 2. So we can write v phi is equals to fr into sin theta. So this is the required equation of v phi. Next, on applying boundary conditions, as r tends to infinity, v phi tends to 0. From this we can see that c1 equals to 0. Similarly, we know that at r equals to r, v phi is equals to r ohm sin theta. On solving this, we get c2 is equals to r cube ohm. So this is the final velocity profile which is required. And similarly for torque calculation, torque is equals to shear stress into area into lever arm, and this is the equation of shear stress, which is tau r phi is equals to minus mu into r into dou by dou r into v phi by r. On substituting v phi, which is here, into this equation, we get this. So tau we integrate as said, tz is equals to shear stress into lever arm into area perpendicular to r direction, which is this, and integrating with proper limits where theta is from 0 to pi and phi is from 0 to 2 pi, we get tz is equals to 8 pi mu ohm r cube. Now, starting with second question, problem states that consider the creeping flow of an incompressible fluid with constant density and viscosity about a solid sphere of radius r. The fluid approaches the fixed sphere with vertically the fluid approaches the fixed sphere vertically upward with the uniform velocity v infinity. Formulate the problem with reasonable valid assumptions indicating all boundary conditions to get the velocity profile. Assumptions are that the flow is at steady state and the fluid is incompressible, which means the density is constant and there is creeping flow where Reynolds number is far less than 1. So all the inertial forces can be neglected and the flow is axisymmetric where v phi is equals to 0 and v theta not equals to 0, vr not equals to 0. As we move away from the sphere, velocity changes, so vr is not equals to 0. Similarly, v theta is not equals to 0 because velocity changes as we move around the sphere. So we can see that vr is a function of r and theta and v theta is a function of r and theta. So on using Navier-Stokes equation in spherical coordinates for a system of constant density and viscosity uh, and solving for phi momentum equation, we get v phi, since v phi is equals to 0 because of symmetric flow, we get 0 equals to 0, which is of no use. Similarly, solving for theta momentum equation, all the left hand side inertial terms will tend to 0 as the flow is creeping. Reynolds number is far less than 1. So this is the equation which remains, and similarly solving for r momentum equation, this is the required equation, and continuity equation for compressible flow, continuity equation for incompressible flow for constant density system and v phi is equals to 0 is this, and as this equation is pretty hard to integrate, we assume stream functions phi in such a way that vr is equals to 1 by r square sin theta dou phi by dou theta and v theta is equals to minus 1 by r sin theta dou psi by dou r, where psi is equals to fr into sin square theta. Now we compute dou psi by dou r, which equals to this, and dou psi by dou theta is equals to this. Similarly, dou by dou theta of 2f sin square theta cos square theta is equals to this. All these have been computed to substitute in the continuity equation. So for creeping flow, we know that delta power 4 psi is equals to 0. We split it in two parts where we compute delta square psi first. Delta square psi first, which comes out to be this, and following the same procedure and applying delta square again, we get delta power 4 psi as this equation, and assuming f is equals to r power n, we get n equals to 0, 1, 3, minus 2. So fr simplifies to be equal to ar cube plus br plus c plus d by r square. So psi is equals to fr into sin square theta. On applying boundary conditions, we get to know that an r square term should exist and a is equals to v infinity by 2, and after solving for that, we get vr is 2 cos theta by r square into ar cube plus br plus c by dr square, and v theta is equals to minus sin theta by r into 3a r square plus b minus 2d by r cube. And applying boundary And as said from boundary condition 2, as r tends to infinity, 2a is equals to v infinity, a is equals to v infinity by 2, and c is equals to 0. From boundary condition 1, vr is equals to v theta, vr is equals to 0 and v theta is equals to 0 at r is equals to r. On solving these both, we can find b and d, and substituting them in vr and v theta, we get velocity profiles of vr and v theta, which is the required thing. Question number 3. Problem states that a copper wire has a radius of 1.234 mm and a length of 1.234 meter. For what voltage drop would the temperature rise at the wire axis be 15 degrees Celsius if surface temperature of the wire is 25 degrees Celsius? Lorentz number for copper is given. On applying energy balance for copper wire and solving for temperature distribution equation, we get this equation, T max minus T naught equals to SC R square by 4K, where SC is given to be this, and after substituting here we get this. And L naught, Lorentz number, L naught is equals to K by Ke into T, and substituting this in this equation, we get T max minus T naught equals to E square R square divided by 4 L naught T naught divided by L square, and E square is equals to 4 L naught T naught L square, T max minus T naught by R square. And solving this, we get E to be this, and substituting the given data in this equation, we get E is approximately equals to 20.41 volt. Coming to next, fourth question. Consider a spherical nuclear fuel element consisting of a sphere of fissionable material with radius RF equals to 5 cm surrounded by a spherical shell of aluminium cladding with outer radius equals to 7.5 cm and constant outer surface temperature is equals to 310 Kelvin. The volumetric heat source due to nuclear fission is approximated by this equation, where the given values are this, and all the given data is listed here, and applying the temperature distribution in fuel sphere and integrating, we get TF as this, and temperature distribution in aluminium cladding to be this, and applying the boundary conditions, we get TF to be this, and substituting the given values, we get maximum temperature in fuel element when R equals to 0, and substituting the given values, we get TF max is equals to 428.99 Kelvin. Similarly, we know TC max is this, and substituting the given values, we get TC max equals to 325.84, which occurs at R is equals to RF.